Good day, folks. In today's class, I'm going to be talking about the half-life of a given substance, and that is from chapter number 16.3. 16.3, half-life. As the name suggests, half-life means in how much time the substance will be a half of its total amount. So if this is a substance, the mass of this substance is, let's say, 1 kg. I'm just trying to give you a simplified view of this. So in how much time it will be half of this total amount. So maybe in 1 year, maybe in 10 seconds, maybe in 2 years, depending upon what kind of a substance it is. So the time period, let's say if it is 1 year, and within 1 year the amount left over will be zero point 0.5. So the half life of that substance will come out to be a 1 year. All right. Now, the formula for the half-life. So N equal to NO, 1 half, then T upon T half. This is the formula to calculate the half-life. In this one, N is the total amount of substance, total amount of substance, and NO is the leftover. Well, I said it wrongly. This is the leftover substance. So this is a leftover, and NO is the total amount of a substance. And 1 half is 1 half. T is the time period, total time or total time period, or you can say total life in easier words, total life of a given substance. And T half is the half-life, as I told you, in how much time the substance will be half of its total amount. That is the half-life. Now, if as I said previously, that if the half-life of a given substance is uh, 1 year, 1 year, so it means in 1 year, this 1 kg substance will, the leftover will be zero point 0.5 kgs. That will be the half-life. Now, after another year, how much substance will be left over? Sometimes we start thinking that, oh, within half time, so this is the substance which was gone, so in the next year, this whole will be gone. No, half-life doesn't work this way. So within the next year, quarter of the substance will be left over. So this portion will be gone. So the substance left over will be 0.25. And half of that in the next year will be left over. And in the next year, half of that will be the leftover. So that's how the half-life works. All right. Another thing which I wanted to tell you with regards to the half-life formula, this formula may not be given to you on your formula booklet, so you can always note down this formula on your formula booklet. The formula given to you is a little different. If you can work with that formula, keep using that formula. That's going to give you the answer also. If you wanted to use this one, you can note down it on your formula booklet too. Now let's dive into a question on the half-life. I'm going to take an example 16.12. Example 16.12 from the same book which you are studying. That is the Pearson Physics Grade 12 for Calgary Board of Education. So example 16.2, that's what I'm taking, page number 813. Page 813. In that example, you are given that the carbon has a half-life. So carbon has a half-life of 5730 years. And how long will it take for the quality of the carbon-14 in a sample to drop to 1/8 of the initial quantity? So in how much time, in how much time the leftover substance will be 1/8 of the original value? So in simple words, if 8 kg was the mass, in how many years the leftover will be 1 kg? That's what the question is. If the half-life is this many years. So I'm going to use the formula N equal to NO 1 half. Then down here it will be T upon T half, and N is what we what is given to me. Actually, n upon no is given to me, so it's given to us in a ratio form. In how much time? 1/8 of the original value will be left over. So how I'm going to write down this one? So n upon no equal to 1/2 t upon t half. That's how I'm going to write it. So n upon no means 1/8 of the substance is left over, and no is the total substance. Okay, and n is the leftover substance. So 1/8 of the total substance is equal to 0.5 raised to the power t, or I'll keep it as 1 over 2 here. So 1 over 2 t divided by 5730. Now, if I see in this question, we are lucky that this number and this number have something common between them. That if I convert 2 raised to the power 3, that's going to come out to be 8. So I can write it as 1 over 2 raised to the power 3 equal to 1 over 2 t 5730. Now, if the base is same, I can compare the exponents. So this kind of a math, if you haven't done the math 182 or 181, so this may be a little tricky for you. That's why I'm solving this question. So if the base of the two terms are same, so for example, if 3 raised to the power x equal to 3 raised to the power 5, means these terms are same, and I can compare the exponents. So x will be equal to 5. So from here I can write it as 1 over 2 are same, so I can write it as 3 equal to t upon 5730. Now I'm going to move this 5730 on the other side. So 3 times 5730 is equal to t, and that's going to be 1.719 times 10 raised to the power 4 years. So in this much time, 1/8 of the substance will be left over. All right, let's look into the practice problem on the same page. So we are given austenite, well, it's not austenite, it's astentine. Sorry for my pronunciation. Astatine. Now, yeah, astatine 218 has a half-life of 1.6 seconds. How long will it take for the 99% of the sample to decay? So we wanted to find the time period for 99% of the sample to decay. All right, so I'm going to write the formula n equal to no 1/2 t upon t half. This is the formula we were using, and I'm going to move this on the other side. So n upon no equal to 1/2 t divided by t half, and n upon no will be equal to, leftover is how much? 99% is decay, so leftover will be only 1%, because this is leftover quantity, and leftover out of total quantity. So that's going to become 0.01. 99% will decay, so leftover is 0.01 out of 100%, equal to 1 over 2 t upon half-life given to us is 1.6. Now, if you see a question like this, this is a little tricky to solve. So I'm going to give you some log formulas. You can note down these formulas on your formula booklet. Mainly the formula you may be using is log a raised to the power n is equal to n log a. That's the formula we're going to be using. So first of all, because the base, I cannot make the base the same, so I have to use the log in this case. So you can note down, as I said, this formula also on your formula booklet. So log of 0.01 equal to log of 1/2 raised to the power t upon 1.6. So here I'm going to bring this down here by using this formula. So t upon 1 upon t divided by 1.6 will go front, and log of 1/2 and log of 0.01. So log of 0.01 is -2, and t upon 1.6 log of 1 half is 0.301 negative, and -2 equal to -3 0.301 t upon 1.6. So what we're gonna do is we're gonna simplify this one, and you're gonna get the value of t as 10.6 seconds, which is approximately 11 seconds. That'll be your answer for the time period. So hopefully you were able to understand how to simplify this kind of a question. So I'm going to quickly look into the other question also, the second one on the same page. So radium-226 has a half-life of 1600 years. What percentage of the sample will be left over after 80,000 years, or 8,000 years, I guess 8,000. So T half is given to you 1600, and total time after 8,000 years, how much will be left over? So N equal to NO, 1 half, this will be 8,000 divided by 1600. So this N upon NO will be equal to 1 half raised to the power 5. So how much is left over? So we are finding out this quantity in the percentage form. N upon NO is what we are looking for. So this is 0.5, or you can say 1 upon 32 also. This goes here, this goes here. 1 raised to power 5 is 1. 2 raised to power 5 becomes 32. So N upon NO will come out to be 0.0312, which is in terms of percentage 3.12125, approximately 5%. This amount will be left over. So hopefully you were able to understand how to simplify these questions, and I'll highly recommend you to do some questions from 814, page 814. And now I'm going to quickly talk about the final concept. Hooray, we are about to finish. So that is